Greetings, everyone. Welcome back. Happy to see you all. Today, I have yet another video, and we are going to be talking about the heartbeat, more specifically, the membrane potentials within the heart that regulate the electrical signals that are propagated all throughout the organ that essentially powers all of your bodily functions because that's what's responsible for delivering oxygenated blood throughout your body. All of that to say, the heart is very important, and we're going to be going over the processes that power the whole process. The questions, the way they were presented, were a little out of order, and so I ended up answering them out of order in these pre-drawn images that I hope you can see. I really hope that you can see. There's really no way for me to tell uh, the way that I'm looking at it right now, but I'm just going to assume that you guys can see it. Maybe if I This has worked every single time before. I don't see why it wouldn't now. So I'm just going to hop into it. The first thing we're going to talk about is action potentials in cardiac ventricular muscles, or cardiomyocytes over here, as well as in the SA or sinoatrial node. So here are the general shapes of the action potentials that we're looking at here. You can see that they're a little different. We have different resting membrane potentials sitting at different depolarized states. We got like a negative 60, you could say, resting membrane potential, negative 90 millivolts here. But the main point that I'm trying to illustrate here is how different cells of the heart are, how they react to an electrical signal in different ways. So I'm going to be going over a little bit on what channels are being opened at these different states that I've labeled. So for phase 4 of the sinoatrial node is, I guess, what you could say where we begin. This is as close as we get to arresting membrane potential. And this is just kind of where it sits as the as the SA node cells are depolarizing until they reach this threshold, as positive ions such as potassium or calcium even are coming into the cell just kind of spontaneously. There's not really any specific uh, special channel that's being opened or activated at this point. That is until we reach phase 0, when we eventually reach that depolarizing threshold, when channels begin to open, starting with the T-type calcium channel. T-type simply refers to a specific calcium channel that reacts very quickly and opens right up as soon as that depolarizing threshold is reached. And that is until we reach sort of our carrying capacity at phase 1 here, where the L-type calcium channel is also opened. I like to think of L-type as latent or longer lasting. And obviously, since it hasn't opened until we've reached this depolarization peak, it is also slower. Kind of like uh, how we've talked about calcium or potassium gated channels in the past. So as they are slower acting, slower to open, though it also suggests that they are slower to close. And so you can see all of these calcium channels are being opened up. They're rushing into the cell from the extracellular fluid that's powering the contraction. That's great. The heart is able to beat now as this sort of wave of positive charges is propagated through the heart. And as I would mention, the potassium the voltage-gated potassium channel. Those are also opened as we reach phase 3, and this is where we start to see positive charges leaking out of the cell, and they're following this electrical ionic gradient, and there's actually ends up being so many positive charges, you could say, being released from the cell that it gets depolarized, and we reach this trough. And the IF that I've written here stands for the funny channel. And the reason they call it the funny channel is because it's a sodium channel that opens as the cell actually gets depolarized, as opposed to getting hyperpol or as it gets hyperpolarized, sorry, as opposed to traditionally we see all these different voltage gated channels being activated as the cell depolarizes and reaches a more positive state, at least in terms of millivolts that we can measure. And that brings us right back to phase 4, and the cycle repeats again. So as we move on to the way that an action potential is propagated in the cardiomyocytes or the cardiac ventricular muscle cells, the shape is quite a bit different. We have a more obvious resting membrane potential here at phase 4, simply illustrating that this is the end of a previous cycle and we're about to reach the beginning of a new one. Before phase 0, you'll see that first we need to depolarize enough. There needs to be enough of a positive charge built up inside of the cell, perhaps from some calcium that's being released from the sarcoplasmic reticulum. Whatever the case may be, a buildup of sodium within the cell, potassium, maybe the potassium leakage channel is blocked up or it's otherwise dysfunctional. All that we and that in the healthy heart cell isn't usually the case. I'm just listing all sorts of different reasons why a positive charge could be built up inside of any cell. But in any case, we reach threshold and we depolarize. We see this relatively steep phase 0. These are all of our voltage gated sodium channels opening up, and sodium's rushing inside of the cell because that's the way the chemical gradient is set up. Our cells they draw in that sodium. Then we reach phase 1, and this is where things really start to kick off. We're going to see all sorts of different channels, mostly involving potassium, starting to open up. We have our initial voltage gated potassium channel opening up, as well as a chloride channel, actually, that's induced by our gradient of calcium. So calcium also comes into the cell, where it rather builds up of the intracellular fluid, and as a result, a special chloride channel opens. So we actually get some negative charges coming in as well. So as I stated before, we have a concentration gradient of sodium that is higher on the outside of the cell. Potassium is the opposite. As voltage-gated potassium channels open, those positive charges rush out of the cell, and we begin to repolarize as the cell becomes more negative in measured charge of millivolts, however you would describe that. So starting in phase 2, we see plethora. I'll just draw a few lines here representing the induction of different potassium channels. But first, I already stated that we had calcium inducing the chloride channel. I should clarify these are L-type calcium channels, as mentioned before, in the SA node action potential. And following that activation of the calcium channel, the L-type calcium channel, we have something called the IKVR. It's really hard to write, so you'll just have to pay extra close attention. I'm only going to be spelling out the letters verbally. IKVR. That stands for the very rapid potassium channel. And the reason we call it very rapid is because they discovered the rapid potassium channel beforehand, but it just so happens to open after the very rapid channel, which would make sense, right? Very rapid has a quicker response than the simply rapid channel in solid out relativity. So we have potassium leaking out of these very rapid and rapid channels, and eventually the slow channel opens up right around here as we're reaching this precipice. The slow channel is slower to open and it's also slower to close. And then finally we have IK1, which is just this internal potassium rectifier. So by rectifier, it means a sort of equilibrium is being reached in the intracellular fluid when it comes to the potassium, to the point where all of the positive charges that were built up on the outside of the concentration gradient are now inside of the cell, and now there's leakage occurring. All of the positive charges will slowly, well, not slowly, but they will inevitably diffuse out of the cell and we will become repolarized again. There is a very high potassium permeability in these cells. So as rapid as it comes in, it can go right back out. The whole purpose of bringing it in just to spit it back out again is to propagate that action potential and send a positive charge to the next cell. We're just, it's like in a relay race. We're just passing the baton to the next cell and we're just kind of forcing the heart to contract all the way down. And that's what's further going to be illustrated. We don't have all the pieces of the puzzle yet, but these are the makings of it. So I'm going to move down, follow this arrow from the action potential of the SA node. And what I have here is what we call an EKG or electrocardiogram tracing. If you've ever seen a heart monitor, you might recognize this shape. If we break it down, we will see that there are several different parts, components of this electrical representation of what's going on in the heart. And we call this the PQRS and T waves. The general concept hasn't changed. We're still looking at voltage. We see slight depolarization here, uh, polarization, a big depolarization representing the propagation of an electrical signal or the contraction of a muscle or a part of a muscle or a part of an organ, and then hyperpolarization followed by repolarizing wave represented by this P area. So the initial bump that we see in the P wave of this signal of our electrocardiogram is the contraction of the atrium, either your left or right atrium. That's where the blood initially enters through a valve. Could be your coming from your vena cava, or it could be going out through your aortic valve, or sorry, your, we're talking about atriums here, where the blood comes in through the valves. So following that depolarization of the P wave, we get sort of a wind up beginning this QRS complex. And this is the real meat of the contraction. This is the ventricle being experiencing tension. You could call it exercise, stress, pressure. The meaning of this story is your ventricle is undergoing a contraction. It is propagating this positive electrical charge. And kind of following the general shape of our SA node, what goes down must come back up again. So this trough that we see here is our S wave, a hyperpolarization. And you could argue it's a sort of overcorrection. And slowly but surely we reach resting membrane potential again. This is really just a story of maintaining homeostasis, propagating a signal every time it's needed, and resetting back to our original state. So what happens if something goes wrong? Let's say that we have the electrodes placed over the heart, we're in the hospital bed, and we don't always see a healthy, regular EKG such as this. Well, as you're laying in that hospital bed, they're going to place a negative electrode, sort of the top, your top right corner of the heart, and a positive electrode, sort of at the apex of the heart on the other side, on your left side. So this is a crude diagram representing your heart. Here's our little sinoatrial node. Here's your right side, here's your left side, your mitral valve, your tricuspid valve. So what happens on the epicardium if we have this sort of injury? Because you have your aorta here delivering oxygenated blood, and your heart, just like any other organ, it needs oxygen to function. So it's going to sort of tax itself. It's going to say, hey, I'm the real breadwinner here. I should get a little bit of the oxygen for my hard work. So as this aorta is stretching down to deliver oxygenated blood in the form of a great big artery, there are capillaries extending from it right back to the heart to feed the epicardium. But if there is a sort of atherosclerosis, if you've been drinking too much canola oil, there may be a buildup, there may be some plaque that is preventing this oxygenated blood from going through the capillaries and reaching the heart. And you can probably guess what happens to muscle or an organ when it's starved of oxygen for too long. There will be some form of necrosis. There will be general wasting away, and you will sustain damage to any part of that organ that is suffering from that clot, from that suffocation. So this is essentially a dead piece of your heart. This is what we call a transmural injury, meaning it goes all the way across the wall, from outside to inside, and all of your cells, all of your cardiomyocytes are dead. There's an overall negative electrical charge being built up. because there's no electrical gradient being maintained within those cells. And whereas the inside of the cell is normally negative, or maintaining a sort of polarized state, the cells are no longer containing that negative charge. It's all of its ions are leaked out, is the best way I can describe it. And we get positive charges building up around this dead area. As your heart propagates a signal from the sinoatrial node, regular sinus current, the way that your heart is supposed to propagate electrical signals and have this bump going from base to apex, we will have sort of what they call a lead. Well, they use leads to trace this, but the general direction that the signal is directing is what we call a vector, meaning direction and magnitude. It's just the path that the signal is following, simply put. If the tail of this vector being negative, because it's coming from the negative electrode, is different from the charge towards where it is heading, I would say. So the tail of your vector is negative and it's heading to a positive position, such as this electrode. You're going to propagate a positive signal. And the inverse is the opposite. So if you are propagating, let's say for your T wave, you're repolarizing, and the tail of your vector is heading generally in this direction. The tail of your vector is negative, but the vector itself is heading back in a negative direction, and you have negative on negative. You are going to see the inverse. And that's exactly what our transmural injury is doing here. And if this were not transmural, were more localized to a small area like this, the effect wouldn't be as severe. It wouldn't be nearly as visible. But if you see your T wave being completely flipped, that's a really good indication of what's going on. There's also another way to tell. We have between our S, as we see up here, our S trough, our hyperpolarization, whatever you may want to call it, and our T wave, there really isn't any recognizable depression at all. We just kind of see this shallow slope. This is what we call an ST elevation, E for elevation. And that's because there's no real hyperpolarization going on. That regular rhythm has been stunted. The heart is no longer able to propagate as strong of a signal because it's kind of negative all the time down here. You know what I mean? You're no longer going from positive to negative. You're going negative to negative, and that's a lot less far of a distance to travel, so to speak, going from negative to negative. So all of this to say, all that I have drawn here, this transmural injury, is what we call a STEMI. That's the diagnosis for it. If we wanted to take all that we have just talked about and summarize it in a word in the operating room, we're going to call that a STEMI. And any other any other non-transmural injury or normal, talking about abnormalities in the heartbeat that aren't as severe as this STEMI is what you would call an NSTEMI, which just stands for not a STEMI. An example of an NSTEMI would be example perhaps an ST depression or a change in the baseline even. So here is our regular resting membrane potential, and it's actually brought upward, changing the baseline entirely. Moving forward, we're gonna talk a little bit about we're not exactly shifting gears, but I want to get into some specific terms: inotropy, lusitropy, and chronotropy. These are all fancy words simply meaning contractility, relaxation, or ability to relax, and heart rate, chronotropy. And what these different endocrinological transmitters, these neurotransmitters, have on the heart and on their processes. Here we have norepinephrine, also known as noradrenaline, calling back to the parasympathetic or to the sympathetic system, rather. And then we have our acetylcholine over here. So let's say we release norepinephrine through the neurons that are connecting these cardiomyocytes, these neuromuscular junctions. The graph makes it pretty obvious outright. We are going to see an increase in our inotropy, or an increase in our contractility, an increase in our lusitropy, or our ability to relax in between those contractions. And the combination of both of those things would naturally lead to an increased heart rate. You're having more contractions, having more relaxations between those contractions as a function of time. You're going to have faster heart rate. And acetylcholine has sort of an inverse effect. So I'm going to break down each of these arrows individually, and I'm going to try to keep this as concise as possible without rambling on. So bear with me. I have a little diagram drawn here. Norepinephrine stimulates beta 1 receptors in the heart, initiating a chain reaction of G proteins, which activate adenylyl cyclase, creating cyclic AMP. Cyclic AMP leads to a couple of different consequences, but one of them is protein kinase A being activated, causing the activation of L-type calcium channels and the RYR channel, which we will get to in a diagram here in a moment. Needless to say, both of these channels being activated result in higher intracellular calcium levels. We're going to get more positive charges built up inside of the cell, as you might recall from previous lessons. If you're looking at the cell, regardless of where in the body it might be, but using the heart in this example, the chemical gradient of calcium on surface level would appear to be much higher in the extracellular fluid as opposed to the intracellular fluid. Meaning when a calcium channel opens on the surface of a cell, calcium will always take that opportunity to rush inside and depolarize the cell. giving it more positive readings of millivolts. However, there's an organelle inside of muscle cells called the sarcoplasmic reticulum that actually has a very high concentration of calcium, even creating an even higher gradient than the intracellular fluid, the cytoplasm, compared to the outside of the cell. So we have sort of an interesting relationship here where calcium coming into the cell breeds even more calcium coming into the cell. And I digress on that point. I think I've said enough about it. Lusitropy, you're gonna depolarize faster. The faster you that's a common theme that we see. The faster that you, kind of like we saw with our rapid acting potassium channels, the faster you can open, the faster you can also close. That continues to check out. So lusitropy is illustrated by the protein kinase A activating, I believe it was called phospholambin. I could be wrong, but there is a lambin, PLB, that's what this stands for. Protein kinase A activating, I'm just going to call it lambin, leading to an increase of calcium reuptake in the sarcoplasmic reticulum. So as I was saying, the circa pump action, the faster a cell is able to hyperpolarize, the faster it is able to depolarize. I that's the way that I like to think of it, at least. So this lambin chemical stimulates the reuptake of calcium into the sarcoplasmic reticulum through the circumpumps. And when you are able to clean up that gradient, you're able to suck all of the intracellular calcium back into this organelle right here into a very concentrated spot. Overall, the cell is going to become hyperpolarized. It's no longer as positive as it was before because these calcium, you have to remember, have two positive charges. So that explains how we're able to relax faster. And then chronotropy, specifically through this mechanism, as cyclic AMP is produced, the more we see the funny channel action going on. And as I stated earlier, funny channels, the reason they are funny is because they open as the cell is depolarized, as it goes back to rest after propagating that contraction and allowing positive cells or positive ions, sodium specifically in this case, to enter back into the cell to repolarize it, as evidenced by the action of our S wave here before our T wave. And I think I forgot to mention earlier, this P wave is specific to the contraction of the atrium, whereas the rest of it is basically just the action of the ventricle that's doing all the work. The atrium is just the entry room of the oxygenated blood. The ventricle is kind of the star of the show. It takes up a lot more room. This is where all of the blood is being pumped. And we're going to talk about what happens as blood enters the chamber and stretches the walls. And I'm excited to talk about that, but fortunately it's at the very end. So that'll be our grand finale. So let's move on. Like I said, I'm trying to keep this short and sweet, but this is an interesting subject to me, so I want to get it right. Is acetylcholine. Whereas adrenaline has a sympathetic effect on our heart, speeds up the heart rate, acetylcholine is more in line with parasympathetic action. which leads to lower rates of inotropy or contractility, lower rates, just slower relaxation, and slower overall heart rate as a result of the two. Acetylcholine is released at the synapse and it binds to, excuse me, our M2 receptors. M2 receptors stimulate the GI protein, which results in a decrease of cyclic AMP being created, and ultimately less activation of the funny channel, meaning that there isn't as much positive ions coming into the cell, and our our action potential finds it harder to become repolarized or depolarized back to resting membrane potential. So that would have to do so relaxation, going back to resting membrane potential, actually has more of a negligible effect, but we can see how that would have an impact on chronotropy, lower heart rate overall. Our contractility is decreased for reasons that are pretty evident by the pathway that we followed with the beta 1 receptor. If we're not having as much adenylyl cyclase being activated, we're not going to get our PKA or our calcium channels activated. We're not going to get calcium entering the cell nearly as much. And we're not going to get a sphere of resonance activating this RYR channel on the sarcoplasmic reticulum to then propagate the signal to the next cell. And that is actually segue into the next thing I wanted to talk about. This SA, this sinoatrial node cell, is kind of the culmination of everything that we have talked about so far. This is where it's all happening. All of the graphs that we've looked at, the diagram of the heart. This is the boots on the ground. So our funny channel, as our negative charges are built up as our action potential reaches hyperpolarization, it opens up. We get our sphere of influence coming off of our initiation of the. Sorry, I'm losing my train of thought. It's getting late over here. Our positive ions coming in, a sphere of influence is being propagated. Here we have our T-type calcium channels. There's nothing necessarily inherent that makes these channels faster acting about their design, as far as I'm concerned, so much as they are just placed closer in proximity to the funny channel, and therefore they're activated by the sphere of influence first. So our calcium comes in following its chemical gradient, as well as the current electrical gradient that we have going on in the cell. Our voltage-gated potassium channels are also being activated, but the gradient of potassium is higher on the inside than it is on the outside, so it's going to be leaking out. We have this excess positive charge being removed, as we saw at the top here. Sphere of influence continues through the cell. We have our L-type calcium channels finally being activated, meaning even more calcium coming in. This influence is being magnified. We have these RYR channels hooked up on the surface of the sarcoplasmic reticulum, and we have our big stores of calcium on the inside of this organelle. So they come out and it's repeated. We have our circopumps that are reuptaking the calcium so we don't ever essentially run out of calcium so that the next signal can be created. Excuse me. We have a gap junction between the SA node cell and the cardiomyocyte, meaning of the signal is propagated very easily. And then we have our old friend, the voltage gated sodium channel being activated. And just as this signal from the first cell is dying out, the good old Na plus will come in and start a little signal of its own. And you will see that there is also a sarcoplasmic reticulum doing much the same thing in this cell. And these cardiomyocytes just continue to keep branching and branching all the way down the heart from base to apex until the T wave goes back the other way and blood is pumped out of the cell. The heart is being forced open and then it's being squished. It's a forceful contraction and then it's followed by a relaxation. Okay, finally, I'm going to end this video off by describing. I don't know why all of my videos are so long, but I guess I'm just being thorough at this point. But I'm going to describe some events taking place specifically in the left ventricle. So that's where the oxygenated blood is coming in to this final segment, the last quarter of the game before it's pumped into the rest of the body. Our left side of the heart. Here we go. So before you see two graphs representing pressure in the left ventricle, and volume as a function of time. That's our x-axis here. We see pressure being built up in the left ventricle, in the left atrium, represented by this different color, and also what's going on with the aorta. And what's important to note, as I was told in class, it's not really the aorta that's being contracted or relaxed because there's very little uh, smooth muscle around the aorta, actually. It's really the capillaries down the way that are doing the work. But nonetheless, it experiences an increase in pressure. So the atrium increases in pressure as blood comes in. That was from the veins that are connecting to the lungs as the deoxygenated blood was snaking its way through the capillaries of the lung and becoming oxygenated near the bronchioles. Bronchioles. So that oxygenated blood is coming into the atrium. We see a good buildup, and as it's being forced in the atrium, we get some flow into the ventricle as well. And we see a pretty we don't see that big of a peak coming into the atrium because it's small. The atrium doesn't have nearly as much room available for blood to come in as the ventricle does. So we get this sort of initial boost of blood coming into the atrium, and as the space fills, you have to keep in mind that it's completely open to the ventricle at this point. So you have this little water balloon expanding, but it's connected to an even bigger balloon. So the little water balloon fills up with fluid, and the rest of it goes into the larger balloon. And as this larger balloon, as you can imagine, blowing up a party balloon, gets filled up, the pressure on the inside builds, and it builds and builds. And as it's expanding, we call that diastole. And we eventually reach a peak until the ventricle can no longer fill anymore. Here's your left side of your heart. It's backwards because it's anatomical position. The blood is coming in. Here's the lungs, and we're going to say that the veins from the lungs are coming in here. The blood that was oxygenated is filling up the ventricle or the atrium, goes into the ventricle. Ventricle starts to become stiff, begins pushing on the walls, and also on these little flaps here. This is our mitral valve. And as the blood kind of bounces off these walls and starts backflowing, it gets caught right here and causes the valve to snap close. And that's our little bump here. So the one and two that I've labeled here is sound one and sound two. The sound one is the sound of the right ventricle getting snapped closed as the deoxygenated blood comes in, snaps, goes out through the pulmonary vein to get oxygenated by the lungs, comes right back in through the left atrium, bounces off the walls, tries to backflow, snap. That's sound two. So we see systole is the contraction happening. And the aorta is experiencing an increase of pressure as well as it's pretty much in line with what the ventricle is experiencing because you can imagine as you have a lot of buildup of oxygenated blood in the ventricle, that would presuppose we also have an increase going on in the atrium. And the aorta is pretty consistent, but we do see an increase in pressure being experienced there. Increased pressure all around. Right here we have what we call the dicrotic notch, which kind of marks the decline of the systole, or the end of systole, I should say. And the what I'm trying to explain next would be best be illustrated by this other graph that we have here, illustrated by volume. So we're measuring in milliliters here, a difference of 70 milliliters. In our left ventricle here, we see an increase in blood volume. And then we see our peak. Then we see a little bit of a plateau here. Right before that plateau starts, we have this little dot, which represents the end diastolic volume, essentially meaning at the end of the period when this ventricle is relaxed, when it's at its largest, when it's letting the most of its blood through. What is that volume at? It's sitting at 120. and we see actually a bit of a plateau. It doesn't decrease right away. That would be indicative of a different problem, which I've written in my notes. That would be our valve failing to close if we saw it decrease right away here. But since the valve, our our AV, atrioventricular valve, is closing, we see a brief pause, no change in the volume of the blood in the ventricle for a brief moment because that valve is being snapped shut, giving our, since it's the left ventricle, that would be our dub, that would be our S2. So our end diastolic volume is 120. And then eventually the blood rushes out of the ventricle back up through the aorta, through the semilunar valve, aortic semilunar valve, and down through that aortic artery, where it can then feed the rest of the body. And as that ventricle is squeezing the blood out, almost being like suctioned out, really, we will reach our end diastolic volume, which sits at 50. End systolic volume minus N, or end diastolic volume minus ESV will give us our overall stroke volume, and multiplying that by our heart rate will give us our overall cardiac output. I hope this video was detailed enough and that I went into sufficient uh, logistics about each of these things, and that it was fairly clear to understand. It's very difficult to draw on Zoom, but I prefer that to using the tiny whiteboard that I have. So thank you all for listening along with me, and I hope that you come away with this understanding a little more about the heart and the way that electrical signals are propagated through it. Thank you for listening, and I hope you have a good night. See ya.